This is section 3.7, rational functions, day 1. A rational function is a function that can be written as a quotient of two polynomials. So we write it as p of x over q of x, where p and q are both polynomials. So to describe behavior of rational functions, these are a little bit different than polynomials because we're going to have asymptotes in here. So this is our parent function, y equals 1 over x. So we still have the x as x goes to infinity, y is going to 0 now. And as x goes to negative infinity, y is also going to 0. Okay, you can see that going along here. It's getting closer and closer to 0, but it's never actually going to touch 0. As x goes to 0, this little plus means from the right side or from the positive side, y is approaching infinity. So as we're going from the right side closer and closer and closer to x equals 0, y keeps getting larger and goes to infinity. And as x approaches 0 from the left side or for the negatives, as it gets closer and closer to 0, y is going closer and closer, or farther and farther down, so it's approaching negative infinity. So vertical asymptotes are vertical boundary lines that the graph approaches but never hits. So if we look on our parent one, we have a vertical asymptote here at x equals 0. So right there, it's a boundary line. A lot of people draw them as dotted lines when they're sketching graphs. It occurs when the denominator of the rational function is equal to 0. Okay, vertical asymptotes, you have to be careful that factors aren't canceling out and that the bottom part actually would be equal to 0. So let's identify vertical asymptotes. So looking at this first function f. So we have f of x equals x plus 3 over x squared minus 9. What I want to do is I want to factor. That's the first thing we should do is factor. X squared minus 9 becomes x plus 3 times x minus 3. Notice that this x plus 3 on top is a quantity. It goes together. We have an x plus 3 on the top and on the bottom. So that would cancel out. So we don't consider x plus 3 for a vertical asymptote. So we take what's left on the denominator and set that equal to 0. So we get x equals 3. That is our vertical asymptote. When you have something that cancels out like this, okay, that means there's a hole in the graph at, in this case, x plus 3 equals 0, so x equals negative 3. So a hole in the graph, this isn't going to look what the actual problem is looking like, but it looks like this where it's going to skip that value and then keep going the way it would. It's like you have a polynomial and you just took one specific point out. So this one has a hole and a vertical asymptote. I'm more concerned about the vertical asymptotes right now. So let's try another example. Let's look at this one. So we have f of x equals that 4x over 5 times the quantity x minus 1 times the quantity x minus 5. This is already factored for us, which is really nice, so we don't have to factor it ourselves. We look to see if anything cancels out, which in this case it does not. So we take the bottom parts and set them equal to 0. So that 5 we don't care about. The x minus 1 set it equal to 0, and x minus 5 set it equal to 0. So this one has two vertical asymptotes, one at x equals 1 and one at x equals 5. All right, and our last example here. F of x equals x squared minus 1 all over x squared minus 2x minus 3. So this one's not factored, so we need to factor it ourselves. X squared minus 1 is x minus 1 and then x plus 1. And on the bottom, x squared minus 2x minus 3. Factors of negative 3 that add up to negative 2. That would be negative 3 and positive 1. Look to see if anything cancels out. Well, the x plus 1s will cancel out. That means there's a hole at x equals negative 1. And then we take what's left on the denominator and set it equal to 0. So x minus 3 equals 0. So our vertical asymptote here is at x equals 3. We also have horizontal asymptotes. So if we go back to our one that we just looked at, the parent function, it has a horizontal asymptote at y equals 0. There are three different types of horizontal, or three different cases we have when we talk about horizontal asymptotes. The first one is if the degree of the denominator is greater than the degree of the numerator. So if we look, the degree of the numerator here is 1, and the degree on the bottom is 2. If that is the case, then you're automatically going to have a vertical asymptote at y equals 0. Okay, nothing fancy. If the bottom is greater than the top, y equals 0. Case 2 is if the degree of the denominator is smaller than the degree of the numerator by 1. So if we look here, the degree of the top is 2. The degree of the bottom is 1. The top is greater by 1. So we have now what's called a slant asymptote. So it's not going to be completely horizontal, it's going to be slanted. So it's the quotient of the rational function. So what that means, we're going to do synthetic division. I'm going to set it up that 3, -2, and 1, with my 1 on the outside. We don't actually care about the remainder here in this case, so forget about it. We only care about these numbers. So we have a slant asymptote here at y equals 3x plus 1. And the last case, case 3, is if the degree of the denominator is equal to the degree of the numerator, then the horizontal asymptote is the ratio of the leading coefficients. So looking here, the degree of the top is 2, degree of the bottom is 2. They're the same. So we have a horizontal asymptote at y equals, the leading coefficient of the top is 3, leading coefficient of the bottom is 1, so it's just the line y equals 3. So let's identify any horizontal or slant asymptotes here. So let's look at this first function g. First, we want to identify the degrees of the top and the bottom. So on here, the degree of the numerator is 3, and the degree of the bottom is 3. So in this case, it's a case 3, where they're equal. So our horizontal asymptote is going to be the line y equals, and then we look at the leading coefficients. So 6 over 2, which is just 3. So there's our horizontal asymptote. All right, looking at the next one. For h, we have a degree of 2 on the bottom and a degree of 1, or the degree of 2 on the top and degree of 1 on the bottom. That's a case 2. So that means we have to do synthetic division. So I'm going to set up the 1, -4, and 1. On the outside, we have -2. And we don't care about the remainder, so forget about it. Here we have a slant asymptote at y equals 1x minus 6. All right, let's look at our last example. K, our degree here on the top is 2, the degree on the bottom is 3. When the degree on the bottom is bigger, then we automatically have a horizontal asymptote at y equals 0. So main idea here is getting a feeling for the three different cases for horizontal asymptotes. The vertical asymptotes, just make sure the denominator, where is the denominator going to be 0?